Go. Okay, so this was our homework on page 27. First, write those in cycle notation. Any disagreements with what's here? Pretty simple. It's interesting that in this case, these two particular permutations commuted. And it's just a matter of when I do sigma rho, which one do I look at first? Rho, right? So I start with rho, A goes to D, and then I see where this guy sends D to B. That's what that. And once I take that first step, now I have to worry about where B goes. So B goes to A, and then this guy sends A to C. So that's my next guy, etc. Right? And when I compose in the other direction, I have to look at sigma first. So A goes to C, but then C goes to B, if you follow it through. Now, why is the order of rho 4? There's an easy way to say this.
It's 4 elements.
What is this?
If you apply it 4 times.
It's a 4 cycle, right? So automatically, this is a cycle notation, right? And so automatically, its order is 4. Because A goes to D, and then the next time it goes to C, and then the next time it goes to B, and the next time it's back to A, and the same thing with all the elements. It's a cycle, right? This represents something that looks like a D, C, B. So it looks like a cycle, and if I run it 4 times, I end up back where I started for everybody. Think of cycle notation as baseball players, right? Easy. So that's the easy case of order. Okay, good. That was homework. Symmetry groups. The connection between geometry and algebra. Beginnings of algebraic geometry. That's really what it is. We established this before, but the symmetries of the triangle, I can obviously rotate this triangle about its center by a third of 360, right, or 120 degrees, and the picture will look the same, except B will end up here and C will end up down there. But there's another way to manipulate this thing geometrically to end up with a triangle that looks the same, again, equal that whole triangle. If I flip it about any of these axes, if I flip it about this axis, A stays fixed, but C and B swap. If I flip about this axis, A and C swap, but B stays fixed, and if I flip about this axis, C stays fixed, and A and B swap. Well, that's S3 that we're looking at. Because what are the elements in S3? They're the 2 rotations left and right, the identity, which doesn't do anything, and 3 swaps. So these are, so S3 is the symmetry group of the triangle. Now, it would be real nice if S4 was the symmetry group of the square, and S5 was the symmetry group of the pentagon, but it's not true. And you can do that yourself. But the problem is, in S4, one of the elements of S4 is that, right? That's a permutation in S4. But if I apply only that to this square, what happens to it?
A and B switch to. Like switch
Well,
A and C.
yeah, but I'm saying I don't switch A and B. Can I do that? Well, if I only switch the top and don't switch the bottom, I've got to rip the thing, right? So that I can twist it like that, and that's not legal, right? I swap the top but not the bottom. I have to at least twist the thing. It's not a square anymore, right? So I can't do that. That's a legal permutation in S4, but it's not the symmetry of the square. And so the symmetries are obvious, right? If I swap BC, as was mentioned, I have to also swap AB. So that's one of them. What's the other one that's like this? That's the flip about this horizontal axis. What would be the flip about the vertical? I mean the horizontal axis here. That's the flip about the vertical. What would be the flip about the horizontal?
DA and CB.
Yeah. DA and CB. And we usually put the lower one first, but it's more normal to write this as AD and BC. It does the same thing, right? And remember, when I use cycle notation like this, what do I really mean by putting these side by side? It's a little different when I'm using cycle notation. Is this a composition of functions? Yeah, it is, because the cycles are always going to be disjoint, but you shouldn't really think about it that way. You should really think about it just as a concatenation of operations, always starting on the right. Well, because the cycles are disjoint, we can always think about it. So what else do we have? I've already taken care of this one and that one. What would be the flip about this diagonal? BD, right? Would be, because if I flip about this diagonal, then A and C stay fixed, right? And then if I flip about the other diagonal, what do I get? I just get AC, right? So here's my four flips, 1, 2, 3, 4. And then obviously I have rotation, right? I can rotate by 90 degrees and the picture will stay the same. And so this is, these are the only legal flips. There's 4 of them, and then I have, I can really think of it as only one rotation, rotate by 90 degrees. So if I rotate by 90 degrees, A goes to B, B goes to C, C goes to D, and D goes to A. That's, well, rotate left, I did it the other way, right? A goes to, I rotated clockwise. A goes to D, D goes to C, A goes to D, D goes to C, C goes to B, and D goes to A. And if I apply it twice, right, this one, A will end up at C, and D will end up at B, and C will end up at A, etc. So I'll end up rotating by 180 degrees. And if I rotate 3 times, A ends up all the way over at B, etc. And that's equivalent to rotating the other direction once. And of course, if I rotate 4 times, I get the identity. So again, the flips, these are all of order 2, right? Order of my flips is 2, and the order of my rotations is order of my rotations 4, right? Because they represent 90-degree rotations. If I rotate 4 times, I get 360 and I'm back where I started. As the famous mathematically deficient company executive said, I'm going to turn this company around 360 degrees. And I think that's what he ended up doing. Okay, so there they are in the non-cycle notation. And this group is called the dihedral group. And the easy way to think about it, it turns out the dihedral groups for any size figure, any regular polygon, are always generated by only two elements. They're generated by a rotate, say RL, and a flip, which, did I call them FAC will work. So in other words, generated by two elements, and this is really good homework, is to finish this table. Just by computing, and you can either use the cycle representations of these or this matrix representation of the things. But it turns out that in general, it's usually written this way: 2n is the symmetry group of the regular polygon, the regular n-gon. So D4 actually has 8 elements. The pentagon symmetry group D5 has 10 elements. And they're always generated this way, by a rotate and a single flip. And you'll get them all by combinations of those. So there's a different, I think we already have in the table a lack of no, we don't have a lack of symmetry. So, but you'll see when you fill this out that this is also a non-abelian group. The dihedral groups starting at D3 are not abelian. So there's a different example of a finite non-abelian group. Okay. Enough of that. The really nasty one is D17. What's special about a 17-sided regular polygon? Historical note, oh, math teachers. 17-sided polygon is inscribed on Gauss's tomb. He considered it the most important thing he did in his whole life, and figured out a way to construct a 17-gon using only compass and ruler, compass and straight edge construction. Considering all that Gauss accomplished, that's kind of an amazing thing. Okay. Okay, cyclic groups and subgroups. The subgroup is a group inside a group. What are the three things we need for subgroups? Closure, identity, and inverses plural, right? Everybody needs an inverse. A cyclic group is a group generated by a single element. So give me a finite non-cyclic group. Non-cyclic group.
Integers?
No. Integers are cyclic, of course, and they're not finite. Finite non-cyclic group. We just left that already, right? D4, right? Of course. Why? Because it takes two elements to generate D4. We just said so. So it's not cyclic. Integers are a cyclic group because they're generated by 1. How do I generate in a cyclic group? I use all powers, including the negative powers. Or the best way to think about it is, if I start with an element, I take it and its inverse and generate all powers, right? If multiplication is the rule, or if addition is the rule, I take all multiples, right? So NZ is generated by N, is a cyclic subgroup of Z. Right, because NZ is a subgroup, and NZ is generated by a single element, N. n minus n. When I do this, I always include that inverse, right? Okay. Every cyclic group's abelian. This is a nice little, again, proof. Suppose A is cyclic. It's generated by a single element, then every element in the group is a power of A, using my multiplicative notation, which you do by default if you don't know abelian. So then x times y is a to the n times a to the m. Remember what this means. This is not integer multiplication. Right? This is really a star a star a star a n times, starred with a star a star a star a m times. So how many a's do I have all lined up? M plus n, right? So that's why this power rule, addition of exponents, still works. But you can't think of it as regular exponentiation because these must be integers. Right? But then, once I get that result, n plus m is the same as n plus n by integer arithmetic. And so I get back, so this, all cyclic groups are abelian. That's an important thing to remember. Okay, your turn. Show that Z5 is a cyclic group by finding a generator. Should be able to write one down. What's the operator in Z5? The operator.
Addition.
Addition, mod 5, right? So, sure. What does 1 look like? Well, it's got 1 in there, and 1 plus 1, right? And 1 plus 1 plus 1. And 1 plus 1 plus 1 plus 1. See how this connects to basic arithmetic? And 1 plus 1 plus 1 plus 1 plus 1, which is 0. And that's the whole group, right? What would 2 be in this group?
2, 4, 1, 3, 0.
That's correct. 4 plus 2 is 6, which is 1. Plus 2 is 3. Plus 2 is 5, which is 0. Yeah. It turns out every non-zero element will generate this group. And why does that work? It won't work in Z6. Why not?
Yes.
Well, what would be 2 in Z6? 2, 4, 0, right? And that's not the whole group. What's the difference?
5 is prime.
5 is prime. Whenever you work in a prime thing here, every non-zero element will generate the group. I think we're finally catching on. Okay, show this S3 is not cyclic by attempting to generate it from each of its elements. This is homework. S3 doesn't have that many elements, right? It's got a rotate left and a rotate right and 3 swaps, right? AB, BC, no commas, sorry, and AC, right? So that's all it's got in the identity for, 6 elements, right? So just do all the powers. Well, we already know the answer, right? Why? Well, if I raise that, if I square that, what do I get? The 2 cycle. What do I get if I square it? Identity. If I square that. Identity. If I square that. Identity. If I cube that. Identity. If I cube that. I never get the whole group out of this, right? It's kind of done. Right? I would need an element of order 6 to generate all of S3, right? S3 is a group of order 6. And none of these elements have order 6. Done. So, okay. Let's just do the beginning of this page, and then we'll just change disks in there. Okay, remember, a relation on two sets, or between two sets, is simply a subset of the Cartesian product. That is, a collection of ordered pairs, any collection of ordered pairs, where the first guy comes from A and the second guy comes from B. Or I can consider a relation on a set to itself, which is a subset of A cross A. A relation on A is reflexive if every element is paired with itself. It's symmetric if for every pair that's in there, its flip is in there. That is, if AB is in there, then BA must be in there. And it's transitive if A is connected to B and B is connected to C, then A must be connected directly to C. So that's the idea of a relation, and the three critical properties, reflexive, symmetric, and transitive. Any relation that has all three properties, reflexive, symmetric, transitive, is called an equivalence relation, and cosets and modular arithmetic are two examples. The equivalence of being membership in cosets, or two numbers being equivalent, mod some thing, are both equivalence relations. So here's an example graphically. Here A is connected to itself, and D is connected to itself, but B and C are not connected to themselves. So this is not
reflexive.
It's not reflexive, right? Reflexive means everybody's connected to themselves. This fails reflexive. Is it symmetric? Why or why not?
C goes to D, C.
Yeah. B goes to C, but C doesn't go back, or C goes to D and D. I'd have to have loop backs everywhere for B. So it fails symmetric. Does it pass transitive?
No.
I mean, a failed example for not transitive.
A goes to B, B goes to C, but C doesn't go to A.
Yeah, A goes to B, B goes to C, I would need a direct connection also. So it turns out when I have all three properties, what it does is creates a bunch of complete subgraphs. What's a complete graph? There's a complete graph of size 2. Everybody's connected to everybody. What would a complete graph of size, sorry about that. Complete graph of size 3 would look like this. Kind of like Mickey Mouse, right? Everybody's connected to everybody. So when I have an equivalence relation, it breaks up the big graph of the relation into a bunch of subgraphs where each subgraph is complete. That's what reflexive, symmetric, and transitive mean. Is once I connect a pair of elements, they have to be all connected this way, and if I connect a third element, all the rest of the connections follow by reflexive, symmetric, and transitive. Okay, good place to pause the video.